Okay, so now we're going to look at some example questions from the handout that you had, the little package. So in that first part, we talked about, now I'm going to change the speed. Let's say we have a 1,000 kilogram car, and it's moving at, I think I said in the front, 20 meters per second. Okay, so what we're going to look at is, what does it look like for the amount of acceleration and the impact forces that exist if this car were to crumple by 1.5 meters or 0.5 meters. So I think from before, you realized we had an equation for the impact, and the equation for the amount of acceleration during an impact was a rearrangement of equation 5, the kinemax equation. Okay, and of course that just comes from the kinemax equation here, which you're all familiar with. So really we just took that and rearranged it to get this formula here. Okay, so we're just going to use that as our sort of guiding principle or guiding equation at this point. So if we substitute in our values, V2, so it comes to a stop, and it crumples in 1.5 meters. The acceleration, if you put this in, so we get 20 squared divided by 2 divided by 1.5 is negative 1, because it's a negative sign there, negative 133.3 meters per second. If we take this now and we take that's a big acceleration. If we take that negative 133.333 divided by 9.8, we're not going to worry about the positive and negative here. It's about 13 or approximately 14 G's of acceleration. So 14 times the acceleration of gravity is how fast that object would come to rest. To figure out the impact force, it's just mass times acceleration. So it's 1,000 times, so we take the 333 times 1,000, and the impact force is about 1, 2, 3, 4, 5, 133,333 newtons of force. Obviously, if it was a bigger object that decelerated at a rate of 133.33 meters per second, it would be a bigger impact force. Okay. What happens if you now make the crumple zone smaller so the car doesn't crumple as much? Well, we use the same governing equation that we had before. The numerator stays the same. The denominator is what changes. The denominator is smaller, so hopefully you were able to predict that your impact acceleration would get bigger. So 400 negative divided by 2 divided by 0.5 is negative 400 meters per second per second. If we take that 400 divided by 9.8, we get approximately about 41 G's of acceleration. 41 times the acceleration of gravity for that kind of impact. Look how much that changed. A drastic amount by just making it so that car didn't crumple as much. So you definitely want to be in this car that crumples more than in that car that crumples less, because the acceleration of the G's you're going to experience are going to be higher. The impact force, same thing. And you just take the 400 times by 1,000. You don't need a calculator to do it. You get negative 400,000 newtons of force. Okay, so all these questions are the same in this package, and you're going to be able to, I'm going to help you with them briefly, and then you're going to finish them yourself. Okay, why would you prefer to be in a car that crumples compared to a car that does not? So again, you can look at the first case where the car crumpled and the acceleration was lower than when the when the car had less of crumpling. If you crumpled it even more, let's say you crumpled it by 2 meters, that's almost into the front of your car, like into your chassis. But if it went by 2 meters, you get even less acceleration. If you decreased it, let's say that the car didn't crumple at all and it was just simply like a 10 centimeter crumple, you would get a massive deceleration, and that would not feel good. Just think about the inertia, like you're moving forward, and you would come to a stop almost instantly. You don't want that. You definitely want that time for the collision to increase. And it says, what is so dangerous about the car does not crumple and simply bounces backwards like a bumper car? Well, a bumper car is not a good thing. Bumper cars, if your car was like a bumper car, your impact time would be extremely small. Your crumple zone would be tiny, and therefore your acceleration would be massive, and your impact force would be massive. You get the whiplash you would get from that is just unbelievable. So answer those two questions there in nice full sentences for the situations. Okay, let's take a look at just how to set up this next question. And then you're going to repeat it, answering the questions that you see there. So we got Big Bang, the stunt beaver, 20 kilogram mass, jumps from a 40-meter high building and lands into a 4-meter thick airbag at the bottom of the fall. He comes to rest 3.5 meters after striking the bag. Okay, so here's the beaver. I'm going to draw him here at the top of the hill. Oh, yeah. There's a drawing. Okay. And he's going to jump, and it's 40 meters to the ground. There's an airbag. So we know that's 4 meters. If the whole height is 40 meters, this is 36 meters. So he falls. He goes, doot, 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 doot. Bam, hits the mat. Then the mat crumples, and it crumples by 3.5 meters. Okay, and that's the amount of crumpling. So he doesn't hit the ground. He's half a meter above the ground. Okay, so now what do we say? Well, the key is that he starts from rest here, and he's going at some speed pretty fast when he hits the mat. Then he comes to rest at the bottom, 3.5 meters in. So let's think about how fast he's going if he dropped from there and just fell. So we go to our first equation. We say, okay, v1 squared. This is always a good one. Let's make down positive just to make life easy. So he starts from rest, so there's no vertical speed. The acceleration is positive because he's accelerating downward with 9.8 meters per second, and his displacement is also positive. If you made up positive, the acceleration would have been negative, as would the displacement would have also been negative, and you'll get the same answer. And so we go 2 times 9.8 times 36, and then we have to square root it, and we take the plus or minus, but since it's moving down, we know the answer is plus or minus 26.56. And we're going to choose the positive value because he's moving down, and we chose down as positive. All right, so that's how fast he hits the mat. Now we just figure out the acceleration. So this is step 1. Now we're in step 2. The acceleration of impact. His acceleration falling was 9.8 meters per second. His impact force is going to be different. So he comes to stop as he falls. He was initially going 26.56 meters. 2, and then the displacement, he displaced himself 3.5 meters in the positive because it's downward. And so that's a displacement of 3.5 meters. So our acceleration is going to be negative because he's accelerating upward and moving downward, which means he's slowing down. 26.56 squared divided by 2 divided by 3.5 is 100.8 meters per second negative. So it means that he's slowing down because he's moving in a positive direction, i.e. downward, and that makes him have a deceleration of negative 100 And then if you multiply that by 20, his impact force is negative 2,015 newtons approximately. Okay, the time of impact we didn't do, but we could figure it out since we know the acceleration. So if we ask for question 3, acceleration is v2 minus v1 over delta t. So delta t is v2 minus v1 over the acceleration. v2 was 0 minus 26.56 is impact speed divided by negative 100.8. So we get 26.56 divided by 100.8. And since they're both negative, you're getting 0.26 seconds of impact. So that's how long it would take to come to a stop. Okay. All the questions are like that. Any kind of questions where objects are falling, this is what you're going to do. So it says repeat the calculation if you crumple only by 0.5 meters. So you can just use the basic equations that we had and to figure out the 3 values if this bag only crumples by 0.5 meters. And then say which would you rather land in and explain by referring to your calculations. Okay, good. You can pause and go back to that and follow what I've done. All right, there's a bungee cord question. It's the same thing. You've got a 70-kilogram person jumps from a 50-high building. The unstretched cord is 25 meters long. So that means that as he falls, for the first 25 meters, there's nothing. There's no impact. So you got to find out how fast he's going after 25 meters of free fall. How fast at this point, this displacement. Okay, and now it says, based on the mass of the person, the cord is calculated to stretch to a length of 45 meters. So it's going to stretch a total of 45 meters, which means that the slowing down part, displacement, is 45 minus 25 is 20 meters of slowing down. Okay, so just like the previous question, assume that he drops from no speed for 25 meters of distance. How fast is he going at that point? Then it stretches 20 meters from there. And so that's his slowing down point. So that's how you can find out his deceleration, or what his acceleration is. And then you can figure out the time and the force as well. And then, explain why you'd want a cord that stretches over a long distance as opposed to one that only stretches over a meter or two. You can use an equation to show that, like we did in the lesson. And then, if you have an ineffective bungee cord that only stretches 2.5 meters, not 20, see what the acceleration would be and what that might feel like. Okay. The last one is standing jump. So let's say that you jump in soft, like I used to do in class, we would do these crumple zone activities. We jump onto force plates and stuff. It's a lot of fun. And when we get back to class, we'll do that. Okay. So when you jump, force of impact, you can jump from a 1.5 meter high desk. You land on the ground. So assume that you drop from 0 and you fall 1.5 meters. Calculate your impact speed, just like we did in question 1. In question 2, do it again here for question 3. Now, the crumpling, the delta D of crumple is 0.3 meters. So you're going to then use that in the second part of it to figure out what the acceleration is if you crumple by 0.3. And then again, what the force of impact is with that. From the next one, you're going to then do it where the same jump of 1.5 meters, but now your crumple displacement is 0.015 meters, and see, that's if you have your legs locked, and see what the acceleration is at this point. And the last part you're going to answer is explain using Newton's laws why you'd want to do this and why you would not want to land with your legs and knees locked. So that could be both talk about in terms of Newton's second law and crumple zones, but also talk about it in terms of inertia. Bodies in motion tend to stay in motion. So if you're moving towards the ground at a fast speed and your body wants to keep going, what might it feel like? Okay, that's your question sheet and the work that you're going to be doing.